Okay, so we are on 17.4, conservation of energy for moving charges. So this equation that I write should look pretty familiar. It's maybe from a while ago, but it still should look familiar. So this is the conservation of energy equation. It's saying that initial kinetic energy plus initial potential energy is equal to final kinetic energy plus, final potential energy. And all of that's saying is that the energy is conserved, and that is still true with the energy of the electric fields, and there's kinetic and electric potential energy for electricity. Sorry about that sound. If you hear it in the background, my fan is so weird. It makes the sound sometimes. See, it's starting again. I don't know. It's weird. All right. And so conservation of energy for moving charges. So changes in gravitational potential energy are often negligible compared with changes in electric potential energy. So when the gravitational force is much weaker than the electric force. So you can do comparison between gravitational force. So that's that universal where you're doing between two different masses. Like, for instance, if I was calculating the gravitational force between, me and my TV right now, we're not that far apart. We're going to have a really small force between us, gravitational force. But if I was doing the electric force between, two charges, a positive and a negative charge in a wire, do you think that they're that far away? No. And we're talking like little tiny bitty things, but the distance is a lot closer, and so your electric force is a lot bigger than what gravitational force would be. Okay, so example 17.8. All right, so this says in an electron gun, electrons are accelerated from the cathode toward the anode, which is at a potential higher than the cathode. So if the potential difference between the cathode and anode is 12 kilovolts, at what speed did the electrons move as they reach the anode? Okay, so first off, I'm going to write this conservation of energy equation. Okay, and the only, hold on, I think I'm going to sneeze. Excuse me. Sorry. Okay, so the only thing that it's giving you right now is this 12 kilovolts. Okay, so I'm going to go over to the other slide, write this out a little bit again. So if you look at like your conservation of energy equation, I don't know why I wrote an equals. Got to ask yourself which one of these kind of cancels out. So at first, the charges are far apart. So do they have initial potential energy? Yes. Do they have initial kinetic energy? No. What about final potential energy? We're actually looking for the speed that the electron is right as it reaches that far anode side. And so the final potential energy basically means that it's gone from one end of that cathode ray to the other, so it doesn't have any potential energy anymore. Okay. Remember that potential energy, one way of writing potential energy is charge times voltage. And remember that that could also be that voltage was equal to electric field times distance. And this was like the work of, so potential energy is equal to the negative work, or negative Q times electric field times distance. is equal to 1/2 mass times velocity squared. Okay? But we're not actually given the electric field, so I don't really know why I put this. Actually, we are given the voltage, so I can just do that. I don't know why I did that. All right, so we're solving for velocity. So velocity is equal to -2 times charge times voltage divided by the mass. Do the square root of that. So you get -2. What is the charge? Well, we're talking about an electron. So 1.6 times 10 to the -19 coulombs. And it's an electron, so it's negative. Times 12,000 volts. Okay, so that was that 12 kilovolts. So 12,000 or 12 times 10 to the third divided by the mass of an electron. Do the square root of all of that, and you should get 6.5 times 10 to the 7th meters per second. Okay, so some equations are the same, some aren't. You just kind of have to figure out what you're given and what you need. So if I were you guys, I would try to make an equation sheet, that's just kind of showing all the different things in this chapter. And I'll do one for you too. I just don't know that I can get it as soon as you need it. I'll try to get one out tomorrow, but we'll see how that goes. And anyway, that could be helpful, I would think, when trying to do these problems. Okay, so now we're on 17.5, which is all about capacitors. So a capacitor is a device that stores electric potential energy. And so sometimes the way I think about a capacitor is I sort of think of them almost like batteries, but they're not batteries. But I like to think of them like that because if you think about a battery stores energy, and that's how we can, put them into things, and then we can get it'll go through a chemical reaction and give us energy and, power things for us. Whereas capacitors have to be charged, and then they hold charge. So almost sort of like a rechargeable battery in a way, even though I still think that those use some chemical energy as well. All right, so it consists of two conductors, which are separated by a vacuum or an insulating material. It could be just air too. Charge is separated with positive charge on one and negative on the other. And typically when you look at a capacitor, it's easy to imagine them just using like parallel plates. And this is a circuit board, for a computer. And it's like craziness, right? It looks like craziness to me too. But there are just all kinds of capacitors on here, even on your keyboard on your laptop right now. When you push the little buttons down, that's creating a charge between those two plates. So there's capacitors all in your keyboard right now too. So definitely useful. Okay, and field lines and a parallel plate capacitor. So if they refer to parallel plate capacitor, they're talking about two different plates, one positively charged, one negatively charged. It's showing you the electric field between the two charges. All right, so that's the simplest form of a capacitor, is a parallel plate capacitor. And they're the simplest to kind of understand because they have pretty much the same area, and they're going to be separated by a distance, and so we can calculate them pretty easy. So charging on a capacitor, one way to charge the plates is to connect the positive terminal of a battery to one. So you're actually using a battery to power these, and the negative terminal to the other. So the battery is going to remove the electrons from one plate, which is going to leave it positively charged and put them on the other plate. That's kind of cool. And they're going to hold that charge for, a certain amount of time. And in order to do this, the battery has to do work, obviously. So if that's the case, then there's some electric potential energy. So chemical energy is converted to electric potential energy, which is what we've been talking about. So because of that, it's going to leave this charge on the surface. And the charge is going to evenly spread on the two surfaces and be in sort of like an equilibrium. And because of that, we have to have another thing. We have a surface charge density, which is given this funny looking symbol right here, which is sigma, and it is the surface charge density, okay, which is the charge per unit area. So we'll get into it as far as looking at unit wise here in a minute. All right. So potential differences between the plates. So obviously if you've got these two parallel plates, one's positive, one negative, there's going to be a potential difference between them. There's going to be a voltage. And so the voltage is equal to the electric field times that distance between the plates. Okay, and the field is proportional to the charge, and the potential difference is proportional to the field. So, and anyway, it was just saying that that's true for all of capacitors. Okay, so another big equation, charge is equal to capacitance. So capacitors have capacitance times the change of voltage, where the charge is the magnitude of the charge on each plate, and the voltage is the magnitude of the potential difference between the plates. Okay, so, the voltage, essentially. And the constant of proportionality capacitance is called, or C is called capacitance. So that's the symbol for capacitance is C. And the SI unit for capacitance is known as a farad. Okay, and so just remember that a capacitance is just how much energy is stored on something, on the plate. Okay? All right, so capacitance of parallel plate capacitors. So a couple more equations, and then I'll probably stop the video, and then we'll do an example. So it says we can define or find the capacitance of a parallel plate capacitor. The electric field is equal to, and this is your charge density divided by, this is not electric field, this is epsilon, which is that permittivity constant. We were given that in chapter 16, so I'll write that down again here in a minute. But that is also, you could also say, because charge density is equal to the charge divided by area. So either way, electric field is equal to both of these. This right here is that. Okay, so surface charge density is, in units wise, is coulombs per meter squared, typically. And this epsilon, this permittivity constant, this is equal to 8.85 times 10 to the negative 12 farads per meter. Okay? All right, so also the A is the surface area of the plate, and the D is the distance. So if you have something that is involving a distance in it, then you could also use this equation. And the electric field here can be given as, because you've got this Q is equal to, this electric field right here is equal to Q divided by A over epsilon. So you could have Q divided by A over that permittivity constant times distance, or it would look like this. Okay, and then by rearranging, you can rewrite it to solve for Q. So if you're solving for Q, then all of it would kind of flip around and give you this times voltage, the change of voltage. Okay, and one more with an equation on, just breaking it down into different ways. So the capacitance of a parallel plate capacitor can be equal to the permittivity constant times the area divided by distance, because, let me show you, we've got charge is equal to capacitance times the change of voltage. On the very previous slide, we said that, I'll write this down here, we said that charge was equal to permittivity times area divided by distance times the change of voltage. Okay, and if we're solving for capacitance here, capacitance is charge divided by voltage. So if I take this and I divide it by voltage, then that cancels, and that's why I'm left with just that. Okay, so that's a little bit crazy, I know. And honestly, it actually breaks down a little bit more even. I almost hesitate to give it to you, except for this is what the book is telling you. Just remember that permittivity was basically K, it was 1 over K. So you could rewrite it like this. And there was a pi in there. It was like 4 pi K times distance. So this is like that. Okay, so it's 1 over 4 pi times K, and K is Coulomb's constant. I can see your faces right now as I'm writing all of this, and I'm sorry. Okay, I will catch you on the